Hi and welcome to the video. In this one we will cover details regarding the code concerning PID controllers. We start by looking at the code I used in last month's video, which is the continuous implementation of the PID controller. Then we take a look at the discrete version of the PID controller, so the version where the controller can only act in predefined time intervals. We further take a limited measurement accuracy into account within the simulation of this approach. Afterwards, I show you simulation results highlighting an issue that can occur because of that. Finally, we close with an outlook. What is meant with continuous simulation is that the controller cycle time, so the time span between two measurements where the calculated controller signal is kept constant, is infinitely small, so the controller can act infinitely fast and is not bound to a fixed time interval. Let's start with the main program. We first perform some housekeeping up here. Clear all variable, close all plots and clear the console. Then we set the plots to use the LaTeX interpreter for all the axis labels and so on. We create a folder to export simulation results to. Here I fetch the standard color definition for creating plots, just to have the same color when using non-standard plot order. Afterwards, we have a short docstring for documentation and continue by defining our system and controller parameters. We use the same gains and times for the continuous and discrete controller, but for the discrete one, we include two additional variables to define the position measurement accuracy. Then we set our simulation end time, target point and initial values for the simulation and can already simulate the continuous implementation using the ODE45 integrator. All we need is a function describing the rate of change of our system, and we take a look at that one next. Since we have a controller as well, we implement both, what the controller does and the dynamic change of the system in the same function. This way we can call a single ODE45 integrator and simulate everything in one go. Let me just bring the equation to calculate the input for the PID controller and the sketch of our system up here for reference, and look where we calculate what and how. In the first step, as always, we separate our state. The first two entries are the states of our system and the last one is the integrated error. We will get to that one in a bit. Let's look at the proportional part first. The proportional part of our controller input is just the difference between our goal point or set point and the actual state of our system, so our measurement of the card position, multiplied by our proportional gain Kp. Then for the derivative part next. Nominally, the controller input for the derivative part is the time derivative of the error multiplied by Kp and Td, as you can see here. We want to control the position, but we have the velocity available as a state. Since the time derivative of the error is equivalent to the time derivative of the goal point minus the time derivative of the measurement, we can use that directly to calculate the time derivative of the error, as you can see here. And we use that to further calculate the derivative part of the controller action. For the integral part last. First, we define to only calculate the integral part if the time ti is not set to 0. This way we can remove the integral part of the controller by setting ti to 0, and we do not have to set it to infinite. I just prefer to do it this way. We calculate the integral action of the controller with the integrated error multiplied by Kp and divided by ti. The integrated error is this back here. And since the ODE45 integrator calculates an integral just like this one here, we can use a trick where we introduce a third state. So this is the third state I mentioned before. The change of this state is just the error between the goal point and the measurement, as you can see here, and in the definition of the change down here. As a result, the third state itself is the integral of the error, which we can use directly to calculate the integral action of the controller. The advantage of the formulation you see here is that our controller acts ideally continuous, since we do not need any numerical approximation for the derivative or the integral. After calculating the individual parts, we combine them to become the full controller signal. Remember, the controller output of the PID controller is just the sum of the components. In the last step of the controller calculation, we limit the output of the controller to the defined saturation limits. Down here, we implement the change of our system depending on the controller action calculated above. And with this, all of the code simulating the continuous implementation of the PID-Controller with the system is completed already. In the main function, we run the ODE45 integrator, then loop over the results a second time down here to recreate the controller signal in order to plot it later on. I would highly recommend you to go through the code yourself as well, if it was a bit too quick. The link is in the description. For the discrete implementation next, I have created a function for this one that returns a state similar to the ODE45 function, as you can see here in the main script. We provide the time steps where we want to simulate, and because of the way it is implemented, this defines our controller cycle time. Let's go inside the function itself. For preparation, we calculate our controller cycle time from the timeline we have to provide, and then we create matrices to export our simulation results. If we want to use quantization, so a limitation of the measurement accuracy in simulation, we set the corresponding variable up here to consider it further down. Here we calculate the analytical solution of the dynamic movement of our system under the assumption that the controller input is constant over a single controller interval, which is the entire idea behind the discrete controller action and the simulation. We do it this way so that we do not have to run an ODE45 integrator for every time step. We can just calculate the result directly. This is just faster to calculate in this way. Next, the interesting part comes, the controller itself. We loop over the time vector provided from outside and go through the same steps each time. First, we extract the current actual position of the card and take the limited measurement accuracy into account. Then we use this to calculate the error between our target position and the measurement. To calculate the integral and the derivative of the error, we use Euler steps as approximation. The integral error is just the integral error from the last time step plus the current error times the controller cycle time. The derivative error is the difference between the error from the last time step and the current error divided by the controller cycle time. This way we calculate the integral and derivative error from the position measurement alone, and we can implement that on a real system just like this as well. Next, we calculate the required controller action for the proportional, integral and derivative part, sum them together and add a feed-forward component if one exists, and we limit the controller output to the saturation limits. Finally, we calculate a single time step. Instead of this line here, you could also run an ODE45 integrator with the dynamical equations for a single controller cycle, like I showed you in the code of a previous video, but this version here, where we use the analytical solution, is faster to calculate. If you are interested in learning more about this, let me know in the comments. In the very last step, we set the last entry of the controller action to be equal to the second last entry to avoid it jumping back to 0 in the plot. This is just so that it looks visually nicer and it has no influence on the actual simulation results. The main function continues after that with plotting of the results. Let's look at the simulation results next and compare the results of the two simulations. I already showed you the results for the continuous simulation and the effect of the different parts of the controller in last month's video. Let's now put the result of the discrete simulation on top and take a closer look. We see two things. First, that the position seems to be identical, and it almost is. But secondly, that our controller input jumps around a lot, especially compared to the continuous simulation. This is not an error in the simulation, this is something that will happen on a real system as well. Let's check out where this comes from. If we zoom into the region back here and we add our actual position and the measured position and controller action, we can see what happens. Because our measurement accuracy is limited, our measurement will always jump around. Always between two possible values. For this example, our accuracy is limited to 1 millimeter, so this is where it jumps around. The controller cycle time of 1 millisecond is visualized with those red crosses added here. Now, every time our measurement jumps, our derivative of the error is massive. Since the measurement jumps by 1 millimeter, our derivative part of the controller will send an impulse into the system, and this repeats throughout. In a real system, the controller will probably just make a sound in this region, and your system will not drive anywhere. If you have experienced it, you know what I mean, and if you haven't, at least you know where it comes from now. There are two ways to counteract this issue. The first one would be to implement an observer and use a reconstruction of the velocity in the derivative part, similar to the continuous controller. And the second one would be to design the controller based on the frequency response of the system, the Bode plot, because this gives more options than the pure PID controller and can help to avoid issues like this. Okay, and that was it already. A little bit more code, but I wanted to go through the implementation quickly. You can find the code on GitHub if you're interested. The repository is linked in the video description. In the next video, I would like to cover the step of the analytical solution a little bit more, what we do here and how you can calculate that. Thank you very much for watching. Like, comment, share and subscribe. Bye for now.